Welcome back. Today we are going through lesson 3.4, which is all about parent functions and their graphs. So to start with, we're going to learn some important terminology that we need to know to help us understand parent functions. So parent functions are a set of basic functions used as building blocks for more complicated functions. We're going to start with the basics, and then we're going to use that to move forward into some more complicated graphs. So some key things we need to know about those parent functions. The continuity is a function with a connected graph. So that's where we're looking for continuous kind of graph as opposed to a segmented one. So if we look at the first graph, we can see that there's no breaks in it or anything. So that would be continuous. The second graph, we would notice that there's kind of some missing parts in here. There's nothing graph for those x values. So this would be a no. And then if we look at the last graph, it goes on forever in both directions. So that's a yes. So continuity means that the graph goes all the way through and there's no breaks. All right, the next thing we have is the x and y intercepts. So the x-intercepts are the points at which the graph crosses the x-axis. So we're looking for those points on the x-axis. So in this case, I can see there's one at -3, 0. There's one, it looks like at 1/2, 0. And there's one at 4, 0. So notice that all x-intercepts have a y value of 0 because they're on the x-axis. Then the y-intercept is just the reverse of that. That's the point where the graph crosses the y-axis. And in this case, we can see that it crosses the y-axis once at the point 0, 2. So y-intercepts have x values of 2, of 0. Y-intercepts have x values of 0. This one happens to have a y value of 2, but their x values are always 0. All right, moving on with our vocab, we also have local maxes and local mins. So if we have more than one local maximum, it's called a maxima. And if we have more than one minimum, they're called minima. So all together, that's the plural. So a local maximum is the highest point on a graph in a given area. So if I sketch a function that maybe, let's say it goes up here, comes back down, goes over here, and then that goes over here, I can see that those high points at the top are those local maxima. So in this case, I can see one of them is at -3, and it's up at 3. And the other one is at 3, 2. So those would be the local maxima. So they're the high points within their area. The opposite of that is the local minimum, which is where we have the lowest points on a graph. So in this case, we have a minimum down there, and that minimum is at 0, -4. So those are maxes and mins, or local mins, local maxes. So as you can see from the maximum, we can have more than one local maximum. All right, when we are talking about functions and their parent functions, we also want to talk about intervals where they are increasing and intervals where they're decreasing. So as you can see from that picture, you can kind of see that guy walking along the graph, and it helps you to think about, would he be walking uphill or downhill as he went? So when the person's walking uphill, that means that the graph is increasing. They're on an interval of increase. When the person's walking downhill, the graph is decreasing. They're on an interval of decrease. All right. When the person is at the bottom or the top of the hill, then they're neither increasing or decreasing. So when they've reached that max or min, they're at the bottom. And so we use parentheses instead of brackets. at those points when we're writing the interval notation. So for this graph, we're going to identify the intervals of increase or decrease. So sometimes it helps me to kind of sketch out. The guy is walking uphill until he gets right here. Then he's walking downhill until he gets to here. And then he's walking uphill again. So he's increasing from 0 to 2. And again, we're using parentheses for that. And so we use the union symbol. He's also walking uphill again from 6 forever to the right. So going forward. Decreasing is in between those. So he's walking downhill from the x value of 2 to the x value of 6. So that's what my notation would look like for increasing and decreasing. All right. Next up, we have our end behavior. This is where we describe what's happening to f of x, which we know is another way of saying y, as the x gets really, really small. So we call that going towards negative infinity. So if we go to the very left side of the graph, where the x's are really, really, really negative, those are really small numbers, or it can also be where it gets very, very large. If we went forever to the right side of the graph, that's where the x values would get really, really big. So that would be positive infinity. So if it helps you, I like to put sometimes on my graph that right side is positive infinity and this left side over here is negative infinity. That helps me kind of visualize what's going on. So looking at some examples here, we write our end behavior in this notation that says as x goes to, so we abbreviate with an arrow, as x approaches or goes to negative infinity. So when we look at the left side of the graph, it's asking where is it going on the y's. So the y's in this parabola are going downwards towards negative infinity. They're getting really small. And then on the right side, as x goes to positive infinity, what's the function doing in terms of y's? So the y values on that right side are going to get smaller also. So they're both ends are going to negative infinity. For the second graph, same thing. We're going to look at what happens as it's going towards the left and what's happening as it goes towards the right. So as x goes toward negative infinity, the function goes over here. My y values are increasing. They're getting bigger, so it's going to infinity. And the right side of the graph is pointing downwards towards negative infinity. So they're getting very, very small. Another thing that may show up on some functions is something called an asymptote. So this is a line that a function gets really, really close to. It approaches it, but it never actually touches it. So if we look at that graph we saw earlier that we said was not continuous, that's because it has this imaginary line. So it's not actually part of the function, but so we draw it as dashed, but it represents the asymptote that function's going to get closer and closer and closer to over here, but it's never actually going to touch it. It's just infinitely getting closer. So we would say that vertical asymptote, because it's going vertical, is at x equals 0. So we want to write it as an equation. And then this function also has a horizontal asymptote. So again, a line that this function is going to get really, really close to, but it's never going to actually touch. So that horizontal asymptote in this case is at y equals 0. All right, and then lastly, we have our domain and range. We should know this one from previous units. So remember, domain is all the possible x values of a function, and range is all the possible y values. All right, so we're going to look through a couple examples here. The first one is a linear function. So a linear function would be something along the lines of a function that just has an x, right? No x squared, nothing funky with it, just a straight x. So that function, when we graph it, we should know that that goes through 0, 0, and then it has a slope of 1. So it's going like that and like that. It should be a straight line. All right. So thinking about the domain, it goes on forever left and right. There's no breaks. So that domain is negative infinity to positive infinity. And the range is also negative infinity to positive infinity. When we look at that graph, we can see that it has no breaks, so it is continuous. And then this one's an interesting one because it goes on forever up and down, so it has no relative max. There's no high point. It just keeps going and going forever. So we just say there is none. Same thing for the minimum. It goes down forever, so it never stops getting smaller or lower. All right. Then intervals of increase. So again, if we think about the guy walking from left to right across the graph, so he would start down here in the left-hand corner and walk upward. He would always be walking upwards. So from negative infinity to positive infinity, he'd be walking upwards, and he would never go down. So there would be no intervals of decrease. All right, then for our end behavior, as we look towards that negative infinity side over here, the graph is going downwards. So that means it's going towards negative infinity on the y-axis. On the right side, it's going upward towards positive infinity on the y-axis. All right, then if we look at some key points. So at -1, it's at -1 because remember the y and the x are the same because the function is f of x equals x. So the y equals the x. So this would be 0, this would be 1, and this would be 2. So my x-intercept would be 0, 0 because that's where the y is 0. And my y-intercept, where the x is 0, is also 0, 0. So this one crosses both axes at 0, 0. So that's the parent function of a linear function. So that's our basic building block that then we could transform from the basic side. The second one we're going to look at is the absolute value function. So the absolute value function is a function. When we write it, the parent function is just the absolute value of x. So again, nothing crazy going on. Parent functions are the basic building blocks. They're the most basic, just the function and an x. So absolute value of x. Remember that the graph of that is centered at 0, 0 and is going upwards to the right and to the left because the absolute value of any number is positive, so it's only going upward. So my domain is all x values. I can plug any x value into the absolute value function. The range on this one, though, only goes from 0 to infinity. It never goes below that x-axis. There are no breaks in this graph from left to right, so that means that it is continuous also. And then maximum, it's going up forever, so there's not a maxima, but there is a minimum. So that's at 0, 0, where it goes to its lowest point. All right, so if we think about our guy walking, when he starts on the left side of the graph, he's walking downwards. So that's an interval of decrease from negative infinity to that minimum at 0. And then he flips and walks upwards from 0 onward. So from 0 to infinity. That means that our end behavior on the left side is pointing upwards towards infinity. And on the right side, it is also pointing upwards. So both ends are going to infinity in the y direction. If I think about my function, so the absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. And the absolute value of 2 is 2. So if we think about my x and y intercept, the y value is 0 at 0, 0 in this function. and the x value is 0 at 0, 0 also. So you can continue on with these notes to look at a few more absolute value functions, and then we'll see you next time.